Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face Trending List, published on December 10th, 2025, just yesterday. It introduces a unified model that understands the scene, reasons in chain-of-thought style, predicts future trajectories, and even generates future driving video, reaching state-of-the-art performance in handling rare long-tail situations much more robustly. The paper is titled UniUGP, Unifying Understanding, Generation, and Planning for End-to-End Autonomous Driving. And as we will see later, the way this model fuses reasoning, planning, and video generation has really exciting implications for safer autonomous driving. Table 1 lays out the landscape of existing autonomous driving models and highlights what the unified approach actually adds. The main body of the table compares world models, vision language action systems, and unified models across reasoning, interactivity with human instructions, and whether they generate future images and trajectories. The header clarifies that reasoning means chain-of-thought explanations, and that interactivity means adapting the trajectory to instructions. The bottom highlighted row shows that UniUGP is the only unified model that both reasons in chain-of-thought style and interacts with instructions, while generating future video using flow matching for its action space. Figure 1 shows how the three hybrid experts work together inside the unified model. The left block depicts the understanding expert, which turns language instructions and history images into hidden states through text tokenization, vision encoding, and multimodal self-attention. The central block illustrates the planning expert, which takes those states plus noised actions and uses flow matching, a technique that gradually denoises actions to predict smooth future velocities. On the right, the generation expert uses A versus AE and a DIT block to denoise latent codes and synthesize future driving images that match the planned trajectory. Figure 2 explains how the team turns raw, long-tail driving clips into rich supervision that teaches the model to think, plan, and follow instructions. The left side shows data collection across accidents, small obstacles, accident relationships, and instruction-driven scenes. The right side illustrates data processing, where questions, future trajectories, and chain-of-thought reasoning annotations are built. Chain-of-thought reasoning means writing out step-by-step explanations, so the model learns not just answers, but why they are correct. The final block converts these annotations into planning and instruction following labels like turn left or go straight. Table 3 shows that the unified model not only reasons better, but also drives more safely than all baselines. The right side reports L2 distance, which measures how far the predicted trajectory is from the ground truth path, so lower values mean more accurate and safer control. The bottom bold row reaches the best understanding scores across small objects, relationships, and accident prediction. Chain of thought scores, where the model explains its reasoning step by step, also peak in that last row. Comparing the two middle rows reveals that removing either chain of thought reasoning or the generation module hurts both planning accuracy and instruction following, confirming that all three experts contribute meaningfully. Table 4 compares how well different driving systems plan trajectories and avoid crashes on the new scenes benchmark. The table shows that the unified model keeps L2 distance, meaning path error in meters, lowest on average, while using only a front camera and question-answering supervision. The right block lists collision rates, where the unified model again achieves the lowest average value. That combination of accurate paths and very few collisions indicates that the model has learned basic traffic rules from simple next frame prediction. Table 5 shows how well different systems generate future driving frames, and it makes clear that the unified model produces the most realistic videos. Frechet inception distance and Frechet video distance are scores where lower values mean the generated images and clips look closer to real data. Across comparable or higher resolutions, the unified model reaches the lowest numbers on both metrics, so it captures scene appearance and motion more faithfully. That improved video realism matters because better visual predictions give the planner a more accurate preview of how traffic and obstacles may evolve. Alright, to wrap up, UniUGP shows that tightly coupling reasoning, trajectory planning, and future video generation can make end-to-end driving systems both safer and more interpretable, especially in rare, long-tail situations. The broader implication is that autonomous cars may increasingly think in words, plans, and imagined futures all at once. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.